Welcome back to Space Repo, your portal to the cosmos. Have you ever dreamt of stepping into a machine, turning a dial, and appearing in a different era? The idea of time travel has captivated humanity for generations, fueling countless stories and scientific debates. But is it just science fiction, or could we one day truly cheat the laws of physics and journey through time itself? At the heart of this incredible possibility lies a concept straight from the mind of Albert Einstein, the Einstein-Rosen bridge, more commonly known as a wormhole. Imagine spacetime not as a flat, rigid stage, but as a flexible sheet of fabric. Now, picture two distant points on this fabric. A journey between them would normally require traversing the entire distance across the surface. But what if you could fold the fabric, bringing those 2 points right next to each other? A wormhole is a theoretical tunnel that does just that, creating a shortcut through the very fabric of spacetime. One end could be here in our solar system, while the other could open up light years away in another galaxy. This isn't just a whimsical idea, it's a potential solution derived from the complex equations of Einstein's theory of general relativity. The theory describes how massive objects warp or curve spacetime, creating the force we experience as gravity. Under certain conditions, these equations suggest that spacetime could become so intensely curved that it forms a tunnel, connecting two separate regions. It would be the ultimate cosmic shortcut, allowing for travel across vast interstellar distances in an instant. But here's where it gets even more fascinating. If you can connect two different points in space, could you also connect two different points in time? The answer, theoretically, is yes. Imagine one end of a wormhole remains stationary, while the other end is taken on a journey at nearly the speed of light. Due to the effects of time dilation, a cornerstone of relativity, time would pass much more slowly for the moving end of the wormhole compared to the stationary one. When the moving end is brought back, it would be younger than its stationary counterpart. For example, if the journey took 10 years from the perspective of the stationary end, only 1 year might have passed for the moving end. You could then step into the younger end of the wormhole and emerge from the older end, effectively traveling 9 years into the future. By reversing the journey, stepping into the stationary end and emerging from the moving one, you would travel 9 years into the past. You have just created a time machine. This isn't magic, it's a logical extension of the physics we already understand. It presents a mind-bending yet plausible mechanism for traversing the fourth dimension. However, as with all grand cosmic theories, there's a catch, and it's a big one. This brings us to one of the most famous and perplexing challenges of time travel, the grandfather paradox. Imagine traveling back in time and preventing your grandparents from ever meeting. If they never meet, your parents are never born, and consequently, you are never born. But if you were never born, how could you have traveled back in time to prevent them from meeting in the first place? This creates a logical contradiction, a loop where the effect eliminates its own cause. The universe, as far as we know, doesn't like paradoxes. They violate the fundamental principle of causality, the law that an effect cannot happen before its cause. Does the existence of such paradoxes mean that time travel to the past is impossible? Not necessarily. Physicists have proposed several intriguing solutions to get around this problem. One idea is the self-consistency principle. This theory suggests that the laws of physics conspire to prevent paradoxes from ever occurring. In this view, you could travel to the past, but you wouldn't be able to change it in any way that creates a contradiction. Perhaps you would try to prevent your grandparents from meeting, but some unforeseen event would always stop you. Maybe you would slip on a banana peel, your time machine would malfunction, or you'd simply find that your actions were part of the history that led to your own birth all along. Free will, in this context, becomes an illusion. The past is fixed and unchangeable. Another, even more mind-bending solution is the many-worlds interpretation of quantum mechanics. This theory proposes that every time a quantum measurement is made, the universe splits into multiple, parallel universes. Each of these universes represents a different possible outcome. When you travel back in time and change something, you don't alter your own past. Instead, you create a new timeline, a new branch of reality. In this new universe, your grandparents might not meet, and a version of you will never be born there. But your original universe, the one you came from, remains completely unchanged. You would simply be a visitor in a new, alternate history that you yourself created. While these paradoxes are fascinating to ponder, there's an even more immediate physical hurdle we need to overcome to make wormholes a reality. Standard wormholes, as predicted by general relativity, are incredibly unstable. They would collapse in on themselves almost instantly, faster than the speed of light. Anything or anyone attempting to pass through would be crushed by the immense gravitational forces. To keep a wormhole open long enough for something to pass through, you would need to prop it open with some kind of scaffolding. But this isn't ordinary material we're talking about. You would need something with properties unlike anything we've ever encountered. You would need something called exotic matter, which possesses negative mass or negative energy density. While normal matter, like the chair you're sitting on or the planets in our solar system, has positive mass and pulls things together through gravity, this exotic matter would do the opposite. It would have anti-gravitational properties, pushing spacetime apart instead of pulling it together. Placing this exotic matter at the throat of a wormhole would counteract the immense gravitational pull, effectively stabilizing the tunnel and holding it open for safe passage. The problem is, we've never directly observed or created stable exotic matter with these properties. While certain quantum effects can create fleeting moments of negative energy density in a vacuum, harnessing it on the scale needed to sustain a human-sized wormhole is far beyond our current technological grasp. It remains one of the greatest theoretical requirements and one of the most significant obstacles standing between us and interstellar, or intertemporal, travel. The quest for time travel is more than just a scientific challenge, it's a journey into the deepest questions of existence. It forces us to confront the nature of time, causality, and our own place within the cosmic tapestry. While we may not be building time machines in our garages anytime soon, the very fact that the laws of physics don't explicitly forbid it is a source of endless wonder. The universe is a strange and magnificent place, and the possibilities it holds may be far more extraordinary than we can currently imagine. Perhaps one day, our descendants will look back at this era as the dawn of temporal exploration. Thanks for joining us on this journey through spacetime. If you enjoyed this exploration, be sure to subscribe to Space Repo for more deep dives into the mysteries of our universe.